Okay, so here we are looking at the next type of reactions. We're going to be looking at synthesis and or combination reactions. I think I guess there could be other names for them, but typically they're going to be called synthesis or combination. Um, yeah, but there could be other names in there as well. It basically just means that you're making something new or you're combining two things together. That's essentially it. And we'll look at the basics, whether we have a unified name or not. Okay. Now these reactions involve smaller atoms and or molecules or compounds combining to form larger molecules. Okay. Now we're going to look at a couple different types, just like we did with combustions. So the type 1 is going to be just elements as reactants. Okay, so just elements as reactants. So two elements combine, but I guess you could have an element and a compound combining together. These are just some small examples. These are just some general examples here of explaining what this type is. Okay? So what can be a heads up for this is that if you see two elements as reactants, there's nothing, you can't break an element down, right? And you can't have displacement when there's only literally two things there. So if you just see two elements of the reactants, you'll know automatically it's a synthesis combination reaction. Okay? But the key thing about this is that there's only one product. That's the major thing here. Okay? There is only one product. And that is what makes synthesis combination reactions a thing. Okay? So these reactions, they produce only one product. No matter what the reactants are, there's only one product. Okay? All right, so let's take, for example, magnesium and sulfur. So two nonmetals. I'd probably have to heat them in most part, but they're going to combine together. So it's a metal and a nonmetal, so these are going to form ionic compound. You would end up with MgS. Okay, now I know this because when these form, it's going to be 2 plus, and it's going to be S, 2 minus. They're equal proportions, so I know it's going to be 1-to-1 ratio. Then I would just make sure to see if they're balanced, and they already are balanced. Okay, now it's ionic. I could probably predict these to be a solid, but we'd have to do it. We'd have to do the reaction to test it out, and so on. These are just theoretical. Okay, so element and element. Okay, now this is a solid here because I know that it's a metal by itself when we're predicting metals to be solids, except for mercury, of course. And then I'll tell you that sulfur at room temperature is a solid as well, and so on. Okay. Example 2 down here. So now we have an element. Now this is still an element, but it's a diatomic. It's an element because there's only one type of thing in there. So even though there's two of those particles, it's still just the same type of particle, which makes it an element, but it is diatomic. Okay. So these two things come together, and they're going to form an ionic compound again. So we know that Mg is 2 plus and N is 3 minus. So you're going to get Mg3 and 2. Okay. And that's just to make sure that they balance, right? Or you can use the crossover method for the easiest way to do it, and that's fine as well. Okay. But the key thing here, right, is that there's only one product, right? So there's only this one, right? Just this one is there. Just this one. And then even when we do this, when we put them together, we're going to get one product as well. These ones make water, and then we'll balance them after, and so on. But again, it's just one product. There's no second product, third product, or anything like that. All synthesis combustion combination reactions end up with one thing, one thing, one thing. Join, one thing. Join, one thing. Join, and then one thing. So this would be what? 3, 2. No, I can't do that. I need 3 of these. 3. That's not going to work either. Let's go with 2, which means 6. That means 4, so then 2. Oh, I guess I could have done just a 3 on there. There you go, never mind. It's already in 2. So you don't want to use higher numbers than you need. So I should get my actual eraser out. I was already balanced with this one at a 2. And 2. All right. So these are all element examples forming one product. Oh, this is make sure this is balanced. 2, and then 2. All right. They can also have compounds as reactants as well. So two compounds, so not just elements, joining to form a single product. And again, it's only one product. Just like the ones with the elements, there's only one product being produced here. Okay. So here we have a non-metallic oxide plus water, and it's going to form a type of acid, and this one's going to be H2SO4, which is our sulfuric acid. Okay. Now, if you looked at them jammed together, you can see that H, right, and then this one just joins over there. Right? Two H's. This one joins over there, and you get that's it. You just cram them together. All right. Now, the key thing to remember, because this is going to come out into play, is that this is how you can actually generate an acid, right? So you take a non-metal oxide plus water. Okay. Now, the other type of example is that you can have a metal oxide plus water, and then this one forms a base. Okay, so in this case here, bases have to have hydroxide, right? So these and that combined, and you end up with CaOH2, which is calcium hydroxide. And this is part of a sequence of events that lead to making acids and bases. Now, there's a little bit more steps involved, depending if you did this as well, but this is the general idea of how you make an acid and bases. Okay, so this is one thing, and this is one thing. Okay, so if you have a non-metal oxide plus water, right? So it's compound, compound, one thing, compound, compound, one thing. Okay. We just have to make sure that everything is balanced, of course, as being good chemists. All right, so 2, it looks like it's balanced. We got 2 and 2, 1, it looks like it's balanced already, so that's good to go. Okay. Now, when you looked at this here, you notice that I use non-metal oxide combined with water forms an acid. Now, how could we produce this? And we already talked about this. This is one of our types of combustion, right? So this was our combustion of a non-metal. Now in this case, it would be sulfur was the non-metal that got combusted and you form a non-metal oxide. This one down here, this is a metal oxide, and you would have got this via the combustion of calcium, right? A metal combustion. All right, I'm going to stay somewhat consistent here. I'm going to change my arrow. There we go. So if I wanted to make calcium hydroxide, I could first combust calcium, which would make calcium oxide, and then I take the calcium oxide I collect and put it in water, and then I'll get calcium hydroxide. Kind of neat. So you take the combustion, and then you use the synthesis reaction of the non-metal oxide plus water to make the base. Okay. See, these are some other examples as well. I'm not. There's clearly a way more than these. These are just the examples that we're going to do and have you practice with, but they can get fairly complex. Okay. So this is just another example. So you can take HCl gas, so hydrogen chloride, and you combine it with ammonia, and you end up with ammonium chloride. Or you can have carbon dioxide plus water, so this is non-metal oxide plus water forming an acid. So combo of small molecules to form larger ones, just as your type 2 up there. All right, so if you had to combine as practice, okay, so this here is a metal oxide. Okay. And I know that metal oxides, when they combine with water, they form a base. So this one is going to be KOH, Co, and then you just have to balance it at that point. So there's 2, let's do it, 2, and then there's 2 there, that's good. Okay. This again is a metal oxide, so I'm going to get MgOH2. All right, then I just have to make sure that they're balanced. 2 H's, 2 O's, that's already good. This is a non-metal oxide, right, plus water. It's going to be, like we saw before, it's going to be H2S, in this case SO3. I just have to make sure they're balanced, and I think they already are. Okay. All right. Decomposition reactions are essentially the opposite of synthesis. So we're going to talk about one and then the other right now because they are opposites. These types of reactions involve the splitting of large molecules into smaller ones. So just like synthesis with smaller ones joining to form larger ones, this is the opposite, large ones breaking down into smaller ones, whether it's elements or compounds or some combination of both. Essentially the opposite of synthesis. Okay. Now, what we're going to take away from this is that if it's the opposite, so synthesis started off by making one product, but the decomposition is going to start off, if it's the opposite, so it's kind of like going in reverse. And this way, you only have one reactant. So anytime you only see one reactant, you know that it's going to be a decomposition reaction, no matter what the reactant is. Although I guess it can't be an element. All right. So here's water. We're going to decompose it. Now, the way that this is usually done is you do something which is called electrolysis. And what electrolysis is, it means that you pass an electrical current through it. So you can have a solution, water or just water, and then you run a current through it, and it will decompose the molecule into its elements. Okay, in this case, it's H and O's. Okay, now these are diatomic, so when they come out, they don't just stay by themselves. They have to be in a diatomic form. Okay, so remember always those H's, O's, Cl's, F's, I's, Br's, and N's. They're all your diatomic. Okay, and then you just have to make sure that they follow into their proper format. Okay, and then you have to make sure they're balanced. So there's going to be a 2 and a 2, and I think that works out fine. Okay. Now this is mercury oxide. This one's pretty straightforward because again, it's going to break down into its elements as well. It just separates into them. Okay, so this can break down into diatomic elements, or you can have a compound that breaks down just into individual elements. Now this one here would be a liquid, I suppose, because that's mercury, and then you have O2, which would be a gas. And this is a metal oxide, so I guess this one would be kind of like a solid as a prediction because it's ionic. Okay? And again, so what we're looking at here, right, there's only one reactant, okay, and that will let us know that it's a decomposition. Over here, the second type is breaking down something into multiple compounds. Now, we're not going to do a lot of this because it's hard to predict, and each different compound behaves differently. It's hard to get general rules, but what you would look for is that you know it's at least decomposition because you have a single thing there. Now, most of the stuff that we're going to decompose are going to tie into these two examples of carbonate and mostly carbonates, but we'll see what happens. You can kind of think of these. It's basically kind of an acid or base breaking down, I suppose, that we saw synthesizing in our synthesis reactions. But let's just look at these two here. So this one will break down into ammonium. Ammonia nitrate will break down to N2O and OH2O. Now, you wouldn't know how to predict that necessarily. So I don't expect you to know, other than remembering that this particular one breaks down into those two things. So this one here would be kind of morally you have to memorize, I guess. But there are rules for certain polyatomics when they break down, but there can be multiple things that they make, and it's hard to predict without actually doing the investigation itself. Now, remember we said at the very beginning of types of reactions, the only way to really know for sure is to do the reaction yourself and then isolate those compounds, which we're probably not going to do. Okay. The carbonates are a little bit more predictable because they always break down into a metal oxide and a non-metal oxide. Okay. So that's at least easier to predict. Okay. So here's two carbonate examples down here. I know I'm going to get a metal oxide and a non-metal oxide, and really it's always CO2. It's always carbon dioxide. So this is the one thing for carbonate. So if it's something that has a carbonate in it, it's always going to have CO2 in the end. Okay. So if I looked at this one here, I can see that's going to be a magnesium oxide. All right, it's a similar format, and then I know that the CO2 remains there. Now this is a solid because it's an ionic compound, and this would be a gas because we know CO2. And this is ionic to begin with, so that would probably be a solid as well. And then we can do the same thing over here with copper. So in this case here, it's copper 2. So it's going to be CuO, CuO, plus CO2 gas. And we just make sure that they're balanced and see if everything's up to snuff. But I think they're already balanced already. Okay? And those are the decomposition reactions.